Hey everyone, and welcome to this explainer. Today, we are decoding the invisible chemical equations that literally power our daily lives. I promise you, once you start seeing the patterns hidden inside these formulas, you're going to start seeing chemistry absolutely everywhere.
So right off the bat, I've got a bit of a riddle for you. What do a fluffy cake baking in your oven, the hard cast on a broken arm, and a bright red fire extinguisher all have in common? I know, it sounds kind of random, right? But the secret actually lies in a brilliantly balanced recipe book of chemistry. It all comes down to how acids, bases, and salts interact with each other.
All right, let's quickly run through our agenda for today. We're going to start by meeting our main characters, acids and bases. Then we'll cover the rules of their chemical reactions, the magic of neutralization, how we create essential salts like baking and washing sodas, and finally, we'll wrap up with plaster of Paris. Let's get into it.
Okay, Section 1. Meet acids and bases, the core ingredients of chemistry.
Let's start by looking at how you can intuitively tell these two apart just based on their physical properties. On the left, we've got acids. They're famously sour. Think of the sharp zing of citric acid in a lemon. They turn blue litmus paper red, and, this is super important for our equations later, they contain hydrogen, or H+ ions. Now on the right side, bases are a whole different story. They taste bitter, they feel slippery to the touch, kind of like soap, and they turn red litmus paper blue. Plus, bases generally contain hydroxide, or OH- ions.
Now check out this setup because it is absolutely brilliant for proving a key property of acids. We're looking at a pretty simple electrical circuit, just a 6-volt battery, a light bulb, and 2 nails sitting in a dilute hydrochloric acid solution. When you close the switch, boom, the bulb lights up. But why? Well, it's because those H+ ions in the acidic solution actually separate out and act as carriers for the electric current. It's just fantastic visual proof that acids conduct electricity.
Moving right along to Section 2, Rules of Chemical Reactions, Understanding the Patterns.
All right, you definitely want to lock this first rule into your memory. It is a massive, overarching pattern. Whenever a metal reacts with an acid, it produces a salt and it releases hydrogen gas. Honestly, if you just remember this one general pattern, you can easily predict the outcome of so many different chemical reactions.
So let's see how that actually plays out with a specific equation. Say we take some solid zinc granules, that's our metal, and we drop them into aqueous sulfuric acid. The zinc basically tags in and swaps places with the hydrogen. As you can see, Zn plus H2SO4 yields ZnSO4, which is our salt, zinc sulfate, plus H2, which is our hydrogen gas. And here's a super fun fact. If you manage to capture that released hydrogen gas and bring a flame near it, it literally makes this really sharp, distinct pop sound.
Section 3. The magic of neutralization, when unstoppable acid meets immovable base.
Okay, here's the visual anchor for what is probably the most crucial rule of all. Acid plus base yields salt plus water. This is an exothermic process, which just means it gives off heat, and it perfectly balances out those two opposing ingredients. Those aggressive H+ ions from the acid pair right up with the slippery OH- ions from the base, and they create totally harmless water, leaving a salt behind.
The really cool part is seeing this interaction in real life. If we take sodium hydroxide, which is a very strong base, and mix it with hydrochloric acid, a strong acid, they completely neutralize each other. NaOH plus HCl gives us NaCl plus H2O. And what is NaCl? It's literally sodium chloride, the regular table salt you sprinkle on your fries. We rely on this exact same neutralization reaction inside our own bodies too. Think about when you get indigestion. Your stomach is making too much hydrochloric acid. You pop an antacid tablet, which is actually a mild base, and it neutralizes the acid to cure your stomachache. Science, right? Let's jump into Section 4, Creating Essential Salts, the chlor-alkali process.
Now, we call this the chlor-alkali process, and it is just incredibly efficient. Step 1, we start with brine, which is really just a highly concentrated solution of salt water. Step 2, we hit it with electrolysis. Basically, we shoot electricity right through the solution. This massive shock breaks the brine apart into 3 hugely important industrial ingredients. At the positive anode, we get chlorine gas, which we use to treat water and make plastics. At the negative cathode, we get hydrogen gas, used for fuel. And what's left over in the water? Sodium hydroxide, a really strong base we use to make soaps. 3 vital products from just 1 puddle of salt water.
Section 5. Baking and washing sodas, the Solvay process to everyday clean. So how do we get these super salts that we all have sitting in our houses right now? We use a multi-stage method called the solvay process. It's a bit like cooking. First, you react ammonia with water and carbon dioxide. Then you take what you get from that and hit it with even more water and carbon dioxide. Finally, you take that whole mixture and react it with plain old sodium chloride. The end result of all this chemical cooking? A white, crystalline powder known as sodium bicarbonate. You probably know it better as baking soda.
Now take a really close look at this equation right here. It's showing thermal decomposition. When you mix baking soda into your cake dough and slide it into a hot oven, that intense heat literally forces the sodium bicarbonate to break down into sodium carbonate, water, and carbon dioxide gas. That CO2 gas gets trapped inside the dough and pushes it upward. That exact reaction is why your cakes rise and get all perfectly light and fluffy.
What's wild is how baking soda basically builds right into washing soda. They're related, but they do very different things. As you can see, baking soda is only mildly alkaline. It's safe enough to eat, to use as an antacid, or to smother a small kitchen fire. But if you take the sodium carbonate that's created by heating baking soda, dissolve it in water, and let it recrystallize, it grabs onto 10 water molecules and becomes washing soda. Now, washing soda is strongly alkaline and highly soluble. It's a hardcore cleaning agent that is absolutely perfect for softening hard water because it tackles calcium and magnesium head-on.
And finally, Section 6, Plaster of Paris, from construction to broken bones.
Yes, I'm talking about plaster of Paris. The chemical formula here is calcium sulfate hemihydrate. We make this stuff by taking a naturally occurring mineral called gypsum and heating it up really carefully to exactly 100 degrees Celsius, or 373 Kelvin. That precise heat forces the gypsum to lose some of its water molecules, leaving us with this fine white powder. And here is where the magic happens. When you break a bone, a doctor takes that exact white powder, adds exactly 1.5 molecules of water back into it, and wraps it around your arm. That triggers an exothermic reaction, giving off heat as the powder rapidly hydrates and sets right back into a solid, rock-hard block of gypsum. It's the same science behind dental molds and even the false ceilings in your house.
Which brings us right back full circle to the riddle we started with. From the fluffy cake rising in your kitchen oven, to the rock-solid cast protecting your broken arm, right down to